Welcome to tonight's journey. Before we drift into the clouds of another world, settle yourself comfortably. Venus awaits, the brightest jewel in our evening sky, hiding beneath sulphuric veils, a story stranger than fiction. Once Earth's twin, now an inferno, this planet holds secrets about creation, transformation, and perhaps the fragile line between paradise and perdition. Tonight, we explore every chapter, every whisper of this enigmatic world. So close your eyes if you wish, let your breathing slow, and allow the tale of Venus to unfold. In the beginning, there was darkness. Then came light, heat, and the slow waltz of creation. 4.5 billion years ago, our corner of the galaxy held no planets, no moons, only a vast cloud of gas and dust spinning lazily through the void. This nebula, enriched by the deaths of ancient stars, contained all the ingredients needed to build worlds. Hydrogen and helium dominated, remnants from the universe's earliest moments, but scattered throughout were heavier elements, forged in stellar furnaces. Silicon, iron, carbon, oxygen, the building blocks of rock and life, waiting to coalesce. At the heart of this swirling disk, gravity drew material inward. Pressure mounted, temperatures soared, and nuclear fusion ignited. Our sun was born, a yellow dwarf star destined to shine steadily for billions of years. Around this newborn star, the remaining disk continued to spin, cooling gradually as heat radiated into space. Within this protoplanetary disk, tiny dust grains collided, stuck together, and grew. Micrometers became millimeters, millimeters became meters. Through countless collisions, these growing bodies swept up more and more material from their orbital paths. This process, known as accretion, unfolded over millions of years. The disk wasn't uniform. Closer to the sun, where temperatures remained high, only rocky materials and metals could condense. Water and other volatiles evaporated, driven outward by solar wind and radiation. This created a natural divide in the developing solar system. The inner regions would birth small, dense, rocky worlds. The outer reaches, where ice could form, would eventually produce gas giants with massive atmospheres. Venus formed in this inner crucible, roughly 70 million miles from the young sun, close enough to receive abundant solar energy, yet far enough to avoid being swallowed by the growing star. The planet grew through a violent process called planetesimal accretion. Kilometre-sized chunks of rock and metal, each following its own elliptical orbit, crossed paths and collided. Some impacts shattered both bodies into fragments. Others, occurring at just the right angle and velocity, resulted in merger. Slowly, through countless catastrophic encounters, Venus gathered mass. The early Venus was nothing like the planet we know today. During its formation, the world existed in a molten state. Impact energy, combined with heat from radioactive decay in the planet's interior, kept the surface liquefied. This magma ocean glowed red-hot, radiating energy into space. Within this molten chaos, heavier elements sank toward the center, while lighter materials floated upward. Iron and nickel descended to form a dense metallic core. Silicate minerals remained in the mantle and would eventually cool to create the crust. Recent research suggests Venus may have formed somewhat differently from Earth, despite their similar final sizes. Computer simulations indicate Venus accreted more rapidly, possibly incorporating more early solar system material before the disk dissipated. This faster formation could have influenced the planet's internal structure and early evolution. The exact sequence of events remains debated, but the basic picture holds. Venus grew from dust, became a ball of molten rock, and slowly, over tens of millions of years, began to cool. As the magma ocean cooled, gases trapped within the molten material began to escape. This process, called outgassing, released enormous quantities of water vapor, carbon dioxide, nitrogen, and other volatile compounds into the developing atmosphere. Early Venus likely possessed a thick atmosphere from the very beginning, far denser than Earth's primordial envelope. This early atmosphere would have been dominated by steam and carbon dioxide, with surface pressures potentially reaching hundreds of times greater than modern Earth. The young Venus might have been shrouded in water. Some planetary scientists believe the outgassing released enough water to form oceans on the cooling surface. If surface temperatures dropped below the boiling point of water, liquid seas could have existed. This tantalizing possibility suggests early Venus might have resembled early Earth, with continents, coastlines, and perhaps even conditions favourable for life. However, Venus's closer proximity to the Sun ensured higher temperatures, and the planet's fate would diverge dramatically from Earth's temperate path. During this formative period, Venus experienced bombardment from leftover planetesimals. The late heavy bombardment, occurring roughly 4 billion years ago, pummeled all inner solar system bodies. Massive impacts scarred surfaces, delivered additional volatiles, and could have stripped away portions of atmospheres. Venus, like Earth and Mars, endured this cosmic assault. Each impact released tremendous energy, vaporizing rock, creating temporary atmospheres of superheated steam and reshaping the young planet's surface. One critical question concerns Venus's rotation. Today, Venus spins incredibly slowly and in the opposite direction from most planets. This retrograde rotation takes 243 Earth days to complete one Venusian day, longer than Venus's year of 225 Earth days. Scientists suspect a massive impact during the planet's formation could have altered its spin. A collision with a Mars-sized body, similar to the impact thought to have created Earth's moon, might have knocked Venus sideways, eventually settling into its current unusual rotation through tidal interactions with the Sun. However, Venus has no large moon. This absence raises questions about its formation history. Did Venus never experience a moon-forming impact? Or did it once possess a moon that was later lost, perhaps spiralling into the planet or being ejected from the system? The answers remain uncertain, hidden in the deep past of planetary evolution. The formation of Venus's interior structure paralleled Earth's development. Differentiation separated the planet into layers. At the centre lies a core, probably composed primarily of iron with some nickel and lighter elements. This core likely has a radius of roughly 3,000 kilometres, about half the planet's total radius. Surrounding the core is the mantle, a thick shell of silicate rock that remains solid near the core but becomes partially molten toward the surface. The mantle comprises the bulk of Venus's mass and volume. Atop the mantle sits the crust, a thin rocky skin that formed as the magma ocean solidified. Venus's crust differs from Earth's in important ways. Earth's crust consists of two types: thick, light continental crust made of granite-like rocks, and thin, dense oceanic crust made of basalt. Venus's crust appears to be uniformly basaltic, lacking the granitic continents that characterize Earth. This difference likely stems from the absence of water-rich environments necessary to create granite through partial melting and metamorphism. Without plate tectonics to recycle crustal material, Venus's surface aged differently from Earth's. The planet's heat budget, the balance between heat generated internally and heat radiated into space, evolved along a unique path. Earth loses heat through seafloor spreading and subduction, where cold oceanic crust plunges back into the mantle. Venus, as we'll explore later, developed alternative mechanisms for cooling its interior. The young Venus, fresh from its violent birth, stood poised at a crossroads. With abundant water vapour in its atmosphere, moderate temperatures, if conditions allowed, and volcanic activity releasing nutrients, Venus might have followed a path similar to Earth's. But subtle differences in distance from the Sun, atmospheric composition, and internal dynamics would compound over geological time, transforming this twin into something unrecognizable. The decisions made by physics and chemistry during those first few 100 million years would seal Venus's fate as the scorching hellscape we observe today. As we drift away from Venus's infancy, imagine that molten world slowly cooling beneath its steamy sky, impact scars healing over time, volcanic mountains rising from lava seas, perhaps even liquid water condensing onto a young warm surface. It's a vision of potential, of possibility, before the runaway greenhouse began its inexorable transformation. Venus and Earth began as siblings, born from the same stellar nursery, shaped by similar processes. Both planets achieved nearly identical sizes. Venus's radius measures roughly 6,050 kilometers, only 300 kilometers less than Earth's. Their masses differ by less than 20%. Their average densities match closely, suggesting similar internal compositions with iron cores and silicate mantles. For hundreds of millions of years, these twin worlds might have followed parallel evolutionary paths. The divergence began with water. Water plays an essential role in planetary evolution, acting as a thermostat for climate, a lubricant for plate tectonics, and a solvent for life's chemistry. Early Venus likely possessed substantial water delivered by icy planetesimals from the outer solar system or released through volcanic outgassing. Some estimates suggest Venus might have held oceans containing enough water to cover the entire planet to depths of tens or even hundreds of meters. But Venus orbited closer to the Sun than Earth, receiving roughly twice the solar radiation. This additional energy proved fateful. As the Sun aged and brightened during its first billion years, Venus absorbed more and more heat. Surface temperatures climbed. Water evaporated more rapidly, filling the atmosphere with water vapor. Here's where the catastrophe began. Water vapor is a powerful greenhouse gas. Unlike oxygen or nitrogen, which let infrared radiation pass through, water vapor absorbs outgoing heat radiation and re-emits it in all directions, including back down toward the surface. This created a positive feedback loop, one of the most destructive climate processes in planetary science. More heat caused more evaporation. More water vapor in the atmosphere trapped more heat. Higher temperatures drove even more evaporation. The process fed on itself, accelerating beyond any stabilizing mechanism's ability to intervene. This is the runaway greenhouse effect, a phrase that sounds almost gentle but describes an apocalypse. On Earth, several factors prevented this runaway. Our greater distance from the Sun meant less incoming energy. When water evaporated, much of it condensed back into rain before accumulating to dangerous levels in the atmosphere. Liquid water on the surface enabled another critical process. Carbon dioxide could dissolve in oceans and react with minerals to form carbonate rocks, permanently removing this greenhouse gas from the atmosphere. This weathering process provided a natural thermostat, preventing Earth's climate from spiraling out of control. Venus had no such safety valve. As temperatures rose past the boiling point of water, everywhere on the surface, the oceans evaporated completely. Without liquid water, carbon dioxide couldn't be locked away in carbonate rocks. Instead, it accumulated in the atmosphere. Volcanic activity continued releasing more carbon dioxide through outgassing. The atmospheric pressure climbed steadily over geological time. The water vapor in Venus's atmosphere faced another threat: photodissociation. High in the atmosphere, ultraviolet radiation from the Sun broke water molecules apart into hydrogen and oxygen. Hydrogen, being extremely light, escaped to space. Oxygen, more massive, mostly remained but reacted with minerals on the surface and in volcanic gases, forming oxides rather than accumulating as breathable air. Over hundreds of millions of years, Venus lost its water inventory to space and oxidation. Recent research has provided intriguing evidence about when this transformation occurred. Measurements of deuterium, a heavy isotope of hydrogen, reveal that Venus's atmosphere has a deuterium to hydrogen ratio roughly 150 times higher than Earth's. This enrichment occurs because lighter hydrogen escapes more readily than heavier deuterium. The degree of enrichment suggests Venus lost an enormous amount of water over its history, consistent with the evaporation of ancient oceans. The timing of Venus's transition from potentially habitable to hellish remains uncertain. Some models suggest the runaway greenhouse began soon after formation, within the first few 100 million years. Others propose Venus maintained moderate surface temperatures and liquid water for up to 2 billion years, well into the Archean eon on Earth, when life was already established. Recent atmospheric modelling, examining nitrogen and carbon dioxide abundances, provides tantalizing hints that Venus might have had plate tectonics in its early history between 4.5 and 3.5 billion years ago. Plate tectonics requires specific conditions. The crust must be relatively cool and brittle enough to break into plates. Water in minerals weakens rocks, making subduction possible. Convection in the mantle must be vigorous enough to drive plate motion. For Venus to have had plate tectonics, surface temperatures would need to be moderate, suggesting the presence of liquid water. If this scenario proves correct, early Venus was remarkably Earth-like, with moving continents, volcanic island arcs, and perhaps even shallow seas. But something changed. The leading theory suggests Venus gradually heated up as the sun brightened, eventually crossing a threshold where water began evaporating faster than it could condense. Once the runaway greenhouse initiated, plate tectonics would have shut down. Without water to lubricate subduction zones, the crust stiffened. Plates stopped moving. The planet transitioned to what planetary geologists call a stagnant lid regime, where a single rigid shell covers the entire planet, unbroken by the kind of plate boundaries seen on Earth. This transition had profound consequences for Venus's long-term evolution. Without plate tectonics to recycle crust and efficiently remove heat from the interior, Venus had to find alternative cooling mechanisms. The planet appears to rely on catastrophic resurfacing events and distributed volcanism to release internal heat, processes we'll examine in detail later. The loss of water affected Venus in another crucial way. On Earth, water in the mantle helps generate our magnetic field. The process works like this. Heat from the core creates convection currents in the liquid outer core. Earth's rotation twists these currents, and the motion of electrically conducting iron generates magnetic fields through a dynamo effect. Water, dissolved in minerals throughout the mantle, helps maintain the temperature gradient necessary to sustain convection in the core. Venus likely had a magnetic field early in its history. Evidence for this comes from the planet's rotation and structure, which should have been capable of generating a dynamo. But Venus today has virtually no intrinsic magnetic field, just a weak induced field created by the solar wind interacting with the upper atmosphere. The planet's core probably still contains a liquid outer portion, but without sufficient convection, the dynamo has ceased. Several factors might explain this. The loss of water from Venus's mantle could have altered heat flow patterns, shutting down core convection. The planet's extremely slow rotation, taking 243 Earth days per revolution, might not provide enough rotational energy to organize fluid motions into a dynamo. Alternatively, Venus's core might have cooled enough that the entire core solidified, though this seems less likely given Venus's size and heat budget. The absence of a magnetic field has ongoing consequences for Venus's atmosphere. Earth's magnetic field deflects most of the solar wind, protecting our atmosphere from being stripped away. Mars, which lost its magnetic field early in its history, has seen much of its atmosphere eroded by solar wind over billions of years. Venus lacks magnetic protection, yet maintains an incredibly thick atmosphere. How? The answer lies in Venus's thick atmosphere itself. While the solar wind does strip away ions from the upper atmosphere, the sheer mass of Venus's atmosphere provides resilience. Losing atmosphere this way is like trying to empty an ocean with a teaspoon. It happens, but so slowly that volcanic outgassing can keep pace. Still, over billions of years, Venus has lost a significant fraction of its water inventory to space through this process. The current atmosphere of Venus stands as the final product of this long transformation. Carbon dioxide dominates, comprising 96.5% of the atmosphere. Nitrogen makes up most of the remainder at 3.5%. Trace amounts of other gases exist: sulfur dioxide, carbon monoxide, water vapor in minute quantities, and various sulfur compounds. Clouds made of concentrated sulfuric acid completely shroud the planet, reflecting sunlight and giving Venus its brilliant appearance in our sky. The surface pressure is crushing, 92 times greater than Earth's sea level pressure. Standing on Venus would feel like being underwater at a depth of 900 meters, nearly a kilometer below Earth's ocean surface. This pressure, combined with temperatures averaging 464 degrees Celsius, creates an environment where lead would pool in molten puddles. The temperature deserves emphasis. At 464 degrees Celsius, Venus is hotter than Mercury, despite being nearly twice as far from the Sun. Mercury, lacking a substantial atmosphere, experiences extreme temperature swings between day and night. Venus, wrapped in its insulating blanket of carbon dioxide, maintains almost constant temperatures day and night, equator to poles. The greenhouse effect is so powerful that nightside temperatures barely drop from dayside values. These conditions make Venus the most extreme terrestrial environment in the solar system, at least on the surface. Yet this hellscape was not inevitable. The same planet, with slightly different initial conditions, or located just a bit farther from the Sun, might have remained temperate. Venus's story is one of positive feedbacks, runaway processes, and irreversible change. It's a cautionary tale written in atmospheric chemistry and planetary physics. Interestingly, Venus's upper atmosphere tells a different story. At altitudes around 50 to 60 kilometers above the surface, temperatures and pressures become remarkably Earth-like. Here, temperatures hover around 0 to 50 degrees Celsius, and pressures approximate Earth's sea level. This habitable zone in the clouds has captivated astrobiologists, wondering if life could exist floating in Venus's atmosphere, even if the surface remained sterile. The transformation of Venus from a potentially habitable world to an inferno likely took place over hundreds of millions of years. It wasn't a sudden catastrophe, but a gradual decline, with each millennium slightly warmer than the last. If life had arisen on early Venus, it would have faced an impossible challenge: adapt to ever-increasing temperatures and acidity, or perish. Did Venusian microbes once swim in those ancient seas? Did they attempt to migrate upward into the atmosphere as the oceans boiled away? These questions remain unanswered, perhaps unanswerable, but they haunt planetary scientists studying our enigmatic neighbour. Approaching Venus from space, a visitor would see nothing of the world below. No continents, no mountains, no valleys. Only an impenetrable shroud of yellowish-white clouds, featureless and forbidding. Venus hides herself beneath the thickest atmosphere of any rocky planet in the solar system. A gaseous envelope, so dense it bends light and conceals all surface features from optical observation. The atmosphere extends far above the surface, thinning gradually with altitude, but remaining substantial even at heights where Earth's atmosphere would be virtually non-existent. The troposphere, the lowest layer where weather occurs, reaches heights of roughly 50 kilometers. Above that, the mesosphere extends to perhaps 90 kilometers, followed by the thermosphere reaching several hundred kilometers above the surface. The cloud layers that define Venus's appearance exist primarily between roughly 45 and 70 kilometers altitude. These aren't water clouds like Earth's, but concentrated sulfuric acid droplets suspended in the carbon dioxide atmosphere. The clouds form through a complex chemical process. Sulfur dioxide, released by volcanic activity, rises into the upper atmosphere where ultraviolet light breaks it apart. The sulfur atoms combine with other compounds to eventually form sulfuric acid, which condenses into tiny droplets. These sulfuric acid clouds are what give Venus its brilliant reflectivity. The planet's albedo, the fraction of sunlight it reflects back to space, reaches about 75%, higher than any other planet in the solar system. This high reflectivity means Venus absorbs less solar energy than Earth despite being closer to the Sun. Yet Venus is still hotter because its thick atmosphere traps nearly all the heat that does make it to the surface. The clouds organize into three main layers, each with different droplet sizes and chemical compositions. The upper cloud layer, between roughly 55 and 70 kilometers altitude, contains smaller sulfuric acid particles. The middle layer, from 50 to 55 kilometers, has larger droplets. Below that, from 45 to 50 kilometers, the main cloud layer exists with the highest concentration of particles. Below 45 kilometers, the air becomes relatively clear, though heat haze makes visibility poor near the surface. Within these clouds, something mysterious occurs. Observations in ultraviolet light reveal dark patches and chevron-shaped streaks that persist for days or weeks. These features absorb ultraviolet radiation strongly, but are bright invisible light. Their composition remains uncertain. Proposed explanations include iron chloride crystals, sulfur particles, or even microorganisms, though the latter seems highly unlikely. The mystery has puzzled astronomers since the features were first observed decades ago. The winds in Venus's atmosphere behave strangely. At the surface, winds blow gently, typically less than a few meters per second. But high in the atmosphere, wind speeds reach extraordinary velocities. At the cloud tops, winds scream around the planet at speeds up to 100 meters per second, roughly 360 kilometers per hour. These winds complete one circuit around Venus in just 4 Earth days, a phenomenon called superrotation. Superrotation remains one of the great unsolved problems in planetary meteorology. On Earth, atmospheric winds generally don't exceed the planet's rotational speed at the equator, but Venus's winds are 60 times faster than the planet's rotation. The atmosphere races around the globe, while the solid planet beneath creeps along at a glacial pace. What drives this extraordinary circulation? The answer involves the interaction between solar heating, atmospheric dynamics, and the planet's rotation. Near the equator, the sun heats the thick atmosphere, causing air to rise. This air flows toward the poles at high altitude. As it moves poleward, conservation of angular momentum causes it to accelerate, similar to how a figure skater spins faster when pulling in their arms. At the poles, the air descends and flows back toward the equator at lower altitudes. But this simple description doesn't fully explain the intensity of Venus's superrotation, and the details remain actively researched. At the poles themselves, remarkable structures called polar vortices exist. These are massive, quasi-permanent cyclones with distinctive S-shaped or double-eyed patterns visible in infrared and ultraviolet images. The vortices show considerable variability changing shape and structure over timescales of days to weeks. They represent a class of atmospheric phenomena with no precise analogue on Earth. The temperature structure of Venus's atmosphere tells another fascinating story. At the surface, temperatures reach around 737 Kelvin, 464 degrees Celsius. Rising through the atmosphere, temperature decreases relatively slowly compared to Earth. This slow decrease reflects the enormous thermal inertia of Venus's dense air. By the time you reach 50 kilometers altitude, temperatures drop to around 300 Kelvin, 27 degrees Celsius, quite comfortable by human standards. Above 50 kilometers, the temperature profile becomes more complex. In the mesosphere, temperatures initially continue decreasing, but then rise again near 90 kilometers altitude due to absorption of solar ultraviolet radiation. In the thermosphere, temperatures climb dramatically, reaching several hundred degrees Celsius. However, the air is so thin at these altitudes that the concept of temperature becomes somewhat abstract. Heat content is minimal despite the high kinetic energy of individual molecules. This temperature structure has important implications. The surface-to-cloud temperature gradient drives vertical convection, with warm air rising from the lowlands and cooler air descending in the highlands. But the convection is gentle, nothing like Earth's violent thunderstorms. Lightning on Venus, if it exists at all, appears rare. Some missions have reported possible lightning signals, but the evidence remains ambiguous. The thick, stable atmosphere damps out the vigorous vertical motions needed to generate the charge separation that produces lightning. The atmospheric pressure gradient is equally remarkable. At the surface, the 92 bar pressure creates near supercritical conditions. Under such extreme pressure, carbon dioxide behaves somewhat like a liquid, with properties intermediate between gas and liquid. The atmosphere's density at the surface is roughly 65 times greater than Earth's at sea level. Ascending through the atmosphere, pressure decreases exponentially. By 50 kilometers altitude, pressure drops to around 1 bar, equivalent to Earth's surface. At 70 kilometers, pressure falls to a tenth of Earth's, and so on. This pressure stratification means any spacecraft descending into Venus's atmosphere experiences steadily increasing loads. The thick lower atmosphere poses immense engineering challenges. Materials must withstand not just high temperatures, but also crushing pressures and corrosive chemicals. Several Soviet landers successfully reached the surface and transmitted data, but survival times ranged from 23 minutes to just over 2 hours before the harsh conditions destroyed them. The composition of Venus's atmosphere holds clues to the planet's volcanic history and interior chemistry. Carbon dioxide dominates, as mentioned, but trace gases provide additional information. Sulfur dioxide concentrations vary significantly over time, sometimes reaching tens of parts per million in the upper atmosphere, other times dropping to near detection limits. This variability suggests ongoing volcanic activity that episodically injects sulfur dioxide into the atmosphere, though definitive proof remains elusive. Water vapor exists in minute quantities, typically around 30 parts per million, roughly 100,000 times less abundant than on Earth. This scarcity reflects Venus's loss of water over billions of years. Carbon monoxide, at around 20 to 30 parts per million, forms in the upper atmosphere through photochemical reactions breaking down carbon dioxide. Nitrogen, though relatively abundant at 3.5%, actually amounts to roughly 4 times more nitrogen in Venus's atmosphere than in Earth's, despite Earth's atmosphere being mostly nitrogen. This reflects Venus's much greater total atmospheric mass. Noble gases provide another window into Venus's history. Neon, argon, krypton, and xenon exist in trace amounts, their ratios offering clues about outgassing history and atmospheric loss processes. The ratios of different isotopes of these elements can reveal whether Venus's atmosphere formed primarily from volcanic outgassing of the interior, or whether cometary impacts contributed significant volatiles. Recent observations have sparked intense debate about another trace gas, phosphine. In 2020, researchers reported detecting phosphine at around 20 parts per billion in Venus's clouds. On Earth, phosphine is primarily produced by anaerobic bacteria or industrial processes, making its presence on Venus potentially significant. However, subsequent analyses have yielded conflicting results, with some teams confirming the detection and others questioning it. The debate continues, with new observations planned to definitively determine whether phosphine exists on Venus, and if so, what produces it. The clouds themselves harbour additional mysteries. Sulfuric acid is highly corrosive, creating an environment seemingly inimical to life. Yet the temperature and pressure conditions in the clouds fall within ranges tolerated by terrestrial extremophile organisms. Could microbes survive floating in Venus's clouds, perhaps shielded within mineral particles or protected by unknown chemistry? The idea seems far-fetched, but nature has surprised us before. The circulation patterns in Venus's atmosphere create distinct climate zones. The equatorial region experiences relatively weak horizontal temperature gradients, with the intense super-rotating winds dominating. Mid-latitudes show more complex flow patterns with eddies and waves. The polar regions, with their persistent vortices, represent yet another distinct dynamical regime. These zones change over time, influenced by the 11-year solar cycle, seasonal variations, and chaotic internal dynamics. Observing Venus's atmosphere from Earth requires specialized techniques. Optical telescopes see only the cloud tops. Radar can penetrate to the surface, but doesn't directly probe the atmosphere. Ultraviolet and infrared observations reveal cloud structures and thermal properties. Ground-based spectrographs can detect specific molecules through their absorption lines. Space missions carrying specialized instruments have provided most of our detailed knowledge, from the Soviet Venera probes to NASA's Pioneer Venus and Europe's Venus Express. The veiled planet keeps many secrets still. How exactly does superrotation maintain itself? What creates the mysterious ultraviolet absorber in the clouds? Could chemical cycles we don't yet understand maintain habitability niches? Venus's atmosphere, thick and opaque, conceals as much as it reveals. Each new mission promises insights, but also typically raises more questions than it answers. For centuries, Venus's surface remained a complete mystery. The thick clouds defeated all attempts at optical observation. Astronomers could determine the planet's size, orbit, and rotation period, but the surface itself remained hidden. Was Venus covered in oceans, as some speculated? Did jungles thrive in a warm, wet climate? Or was the surface completely inhospitable? The answers had to wait for the development of radar technology and spacecraft capable of penetrating the clouds. Radar changed everything. Radio waves passed through Venus's atmosphere with relative ease, reflecting off the solid surface and returning information about topography, roughness, and composition. In the 1960s and 1970s, Earth-based radar systems began mapping portions of Venus's surface with limited resolution. These early maps revealed a relatively smooth planet with some elevated regions and what appeared to be volcanic features, but details remained scarce. The revolution came with spacecraft missions equipped with radar. NASA's Pioneer Venus orbiter, arriving in 1978, carried a radar altimeter that measured elevation across the planet, creating the first global topographic map. Soviet Venera 15 and 16 orbiters, arriving in 1983, used synthetic aperture radar to image the northern hemisphere at resolutions of 1 to 2 kilometers. These missions revealed a world of volcanoes, mountains, and bizarre geological features unlike anything seen on Earth or other planets. But the definitive mapping campaign came from NASA's Magellan spacecraft. Launched in 1989 aboard Space Shuttle Atlantis, Magellan entered Venus orbit in August 1990 and spent 4 years systematically radar mapping the planet's surface. Magellan achieved resolution as fine as 120 meters, comparable to optical images of other worlds. The spacecraft eventually mapped 98% of Venus's surface, returning more data than all previous planetary missions combined. What Magellan revealed was stunning. Venus's surface divides into 3 broad categories of terrain. Lowland plains, sitting below the planet's mean radius, cover roughly 20% of the surface. Rolling uplands and extensive volcanic plains occupy roughly 70%, forming the planet's characteristic landscape. Highland regions, rising more than 2 kilometers above the mean radius, account for only about 10% of the surface. This distribution differs markedly from Earth, where elevation shows a bimodal distribution with deep ocean basins and high continents. Venus's elevation distribution is much more concentrated around the mean, giving the planet an overall smoother topography. 2 major highland regions dominate what passes for Venus's continental masses. Ishtar Terra, located in the northern hemisphere, spans roughly the size of Australia. This elevated plateau rises several kilometers above the surrounding plains and hosts Venus's highest mountains. Maxwell Montes, part of Ishtar Terra's eastern border, reaches an elevation of 11 kilometers above Venus's mean radius. Taller than Mount Everest rises above Earth's sea level. The mountain range shows clear signs of compressional deformation, with parallel ridges and thrust faults indicating crustal shortening. Aphrodite Terra, straddling Venus's equator, extends even larger, roughly the size of South America. This highland region shows more varied topography than Ishtar, with deep rifts, volcanic features, and highly deformed terrain. Unlike Ishtar's relatively smooth plateaus, Aphrodite appears more fractured and complex. The region represents one of Venus's most geologically active areas, or at least was in the relatively recent past. The mountains of Venus differ fundamentally from Earth's. On our planet, most major mountain ranges form through plate tectonics, where colliding plates crumple crust upward. The Himalayas, Alps, and Andes all owe their existence to plate convergence. Venus lacks plate tectonics, yet possesses impressive mountains. How did they form? Maxwell Montes likely represents crustal thickening through compression, possibly driven by mantle convection patterns. Horizontal forces in the lithosphere could have crumpled and folded the crust, building mountains without requiring full plate tectonics. The mountain belt shows characteristics reminiscent of terrestrial fold and thrust belts, with parallel ridges spaced several kilometers apart. Some researchers propose the region formed over a mantle upwelling, where hot material rising from deep within compressed and elevated the overlying crust. Beyond the highlands, Venus's lowlands and rolling plains tell their own stories. The surface is dominated by volcanism. Roughly 80% of Venus shows volcanic features, from vast lava plains to individual shield volcanoes. Over 1,600 major volcanic centers have been identified, with diameters exceeding 20 kilometers. The true number of volcanoes, including smaller features, might exceed 1 million. Venus, quite simply, is a volcanic planet. The volcanic features come in many forms. Shield volcanoes, broad and gently sloping like Hawaii's Mauna Loa, are common. These form when highly fluid lava erupts repeatedly from a central vent, building the mountain through successive flows. Some Venusian shields rival the largest volcanoes in the solar system. Mont Mons, the tallest volcano on Venus, rises 8 kilometers above the surrounding plains and spans hundreds of kilometers at its base. Unique to Venus are volcanic features called pancake domes. These circular structures, typically 20 to 25 kilometers across and several kilometers high, have flat tops and steep sides. They likely formed from eruptions of very viscous lava that oozed out slowly, piling up around the vent rather than flowing far from the source. The smooth pancake-like appearance suggests the lava had a consistency similar to thick bread dough, perhaps caused by high silica content or simply cooling rapidly in the extreme surface conditions. Another distinctive feature class is coronae. These quasi-circular structures range from 60 to over 2,000 kilometers in diameter, with most falling in the 100 to 300 kilometer range. Coronae show concentric rings of ridges and troughs, often surrounded by radial features extending outward. They're thought to form over mantle plumes, where hot material rises from deep within Venus. The plume uplifts the crust, creating a bulge. As the plume spreads and cools, the surface subsides, forming the characteristic circular fracture patterns. Over 500 coronae have been catalogued on Venus, far more than on any other terrestrial planet. Arachnoids present yet another unique feature. These structures, named for their spider-like appearance, consist of central volcanic features surrounded by networks of radiating fractures. They range from 50 to 230 kilometers across. The formation mechanism likely involves dike injection, where magma forces its way through cracks in the crust, creating linear features radiating from a central point. Arachnoids might represent an earlier stage in corona formation, or they might form through a related but distinct process. The most ancient-looking terrain on Venus comprises the tesserae. These intensely deformed regions show complex patterns of intersecting ridges and grooves, creating a jumbled, chaotic appearance at scales from kilometers to hundreds of kilometers. Tessera terrain sits generally higher than surrounding plains and appears heavily fractured in multiple directions. The name comes from Greek, meaning tiles or mosaic patterns, describing their appearance in radar images. Tesserae likely represent the oldest exposed crust on Venus, predating the extensive volcanic resurfacing that covered most of the planet. They might be fragments of an ancient crust perhaps formed when Venus was cooler and had different tectonic processes operating. The intense deformation suggests tesserae experienced compression, extension, and shearing forces, possibly during multiple episodes of crustal movement. Alpha Regio and Ovda Regio are among the most prominent tessera regions, showing particularly complex deformation patterns. Impact craters provide crucial information about surface age. Venus has roughly 1,000 catalogued impact craters, far fewer than the Moon or Mercury, but more than Earth. The craters range from 3 to 280 kilometers in diameter. Notably, no craters smaller than 3 kilometers exist on Venus. The thick atmosphere filters out small impactors, breaking them apart through friction before they reach the surface. Only asteroids or comets large enough to survive atmospheric passage create craters. The crater population tells a surprising story. The craters appear randomly distributed across the surface, with no concentration in particular regions. Moreover, very few craters show signs of significant modification by volcanic flooding or tectonic deformation. This distribution suggests the entire surface of Venus is roughly the same age, approximately 300 to 500 million years old. This finding shocked planetary scientists when Magellan revealed it. On Earth, surfaces show ages ranging from fresh basalt, just solidified, to ancient cratons billions of years old. The variation reflects active geology, with different regions experiencing volcanism and mountain building at different times. Venus, however, appears to have been resurfaced globally in what some researchers call a catastrophic resurfacing event. Between 300 and 500 million years ago, extensive volcanism may have buried the older, more heavily cratered surface beneath lava flows, creating the relatively young surface we observe today. Not all scientists accept the catastrophic resurfacing model. Alternative hypotheses propose that Venus's surface ages vary more than the uniform crater distribution suggests, but lava flows have preferentially covered or erased older craters, or perhaps volcanism has been more continuous than catastrophic, with ongoing eruptions maintaining a relatively constant crater density at equilibrium between crater formation and obliteration. The debate continues, with both models able to explain aspects of the observed geology. The plains that dominate Venus's landscape show varying textures and brightness in radar images, indicating different surface properties. Smooth plains appear dark in radar, suggesting relatively flat, unweathered surfaces. Wrinkle-ridged plains show patterns of long, sinuous ridges created by compression of solidified lava flows. Ridged plains display more intense deformation with closely spaced ridges. These variations likely reflect different ages, compositions, or cooling histories of the volcanic deposits. Lava flows extend for hundreds or even thousands of kilometers across Venus's surface. Some flows show distinct channels where lava carved paths through earlier deposits. These channels, sometimes several kilometers wide and hundreds of meters deep, indicate extremely fluid lavas with low viscosity. The long run-out distances suggest either very high eruption rates or exceptionally hot lavas that remained liquid over great distances. One particularly intriguing class of features comprises the long, sinuous channels called coronae. The longest of these, Baltis Vallis, extends nearly 7,000 kilometers, making it the longest known channel in the solar system. These channels meander across plains, sometimes splitting and rejoining, creating braided patterns. They likely formed from extremely fluid lava, possibly molten sulfur, or very hot basaltic magma. The formation of such extensive channels requires sustained eruptions maintaining flow over long periods, perhaps years or decades. The surface composition of Venus remains somewhat uncertain because we have samples from only a handful of landing sites. The Soviet Venera landers that reached the surface carried instruments for chemical analysis. Venera 13 and 14, landing in 1982, found basaltic compositions similar to oceanic basalt on Earth, with high iron and magnesium content. Venera 8, landing in 1972, analysed rock from an elevated region and found higher potassium content, suggesting more evolved compositions similar to granite. More recent analysis of radar and infrared data from Venus Express suggests compositional variations across the surface. Highland regions might contain more felsic rocks, richer in silica and aluminum, while lowland plains comprise more mafic basalts, rich in iron and magnesium. These variations, if confirmed, would indicate diverse magmatic processes, with some regions experiencing partial melting and crustal differentiation, similar to what produces continental crust on Earth. The radar brightness variations observed by Magellan revealed another mystery. Many mountainous regions show unusually high radar reflectivity above certain elevations, typically around 4,500 to 5,000 meters. This sharp boundary suggests a coating of some material that reflects radar strongly. Proposed explanations include metallic frost, perhaps iron pyrite, or other metal-bearing minerals that become stable under the cooler temperatures at high elevation. Alternatively, the coating might be a weathering product formed by different chemical reactions in the thinner atmosphere at altitude. Some surface features indicate tectonic forces have shaped Venus's crust, despite the absence of plate boundaries. Fracture zones called chasmata create deep rifts cutting through the landscape. Diana Chasma, associated with Diana Corona in the southern hemisphere, drops several kilometres below the surrounding terrain. These rifts might represent extensional features, where the crust pulled apart, similar to Earth's continental rifts, like the East African Rift. Mountain belts on Venus show signs of compression, with parallel ridges and thrust faults indicating horizontal shortening of the crust. These features formed without subduction zones or colliding plates, probably through vertical motions in the mantle creating regional compression. The scale of deformation, while impressive, falls short of the crustal recycling and mountain building accomplished by Earth's plate tectonics. Weathering on Venus proceeds slowly. The surface temperature remains stable at around 464 degrees Celsius, with minimal diurnal or seasonal variation. Without liquid water, many weathering processes common on Earth don't operate. However, chemical weathering through reactions with atmospheric gases still occurs. Minerals react with carbon dioxide, sulfur dioxide, and other compounds. Some minerals, stable at lower temperatures, decompose or alter chemically in Venus's extreme heat. Wind erosion, though gentle due to the dense atmosphere creating high resistance to motion, nevertheless moves particles slowly across the surface. Dune fields have been identified in some regions, indicating wind-blown sediment transport. The particles move sluggishly through the thick air, but over geological time, significant erosion and deposition can occur. Some rocks show streamlined shapes suggesting sand blasting by windborne particles. The revealed surface of Venus presents a world frozen in volcanic time. Mountains rise without plate tectonics. Volcanoes crowd the landscape in numbers exceeding all other terrestrial planets. Unique features like coronae and arachnoids betray the planet's unusual thermal evolution. The relatively young age suggests Venus might experience episodic resurfacing, with quiet periods interrupted by catastrophic volcanic episodes. Or perhaps volcanism continues steadily, maintaining a dynamic surface that conceals its ancient history beneath fresh lava. Standing on Venus, if one could survive the heat and pressure, the landscape would stretch flat in most directions, broken occasionally by distant mountains or volcanic domes. The sky would glow orange from scattered light, filtering through the thick clouds far overhead. Visibility would extend perhaps a kilometre before heat haze obscured the view. No stars would shine, no wind would blow, just stifling stillness. The surface, revealed at last by radar eyes, shows a world of fire, pressure, and strange beauty that exists nowhere else. Venus burns, not with flames, for oxygen barely exists at the surface, but with heat rising from the planet's interior, driving geological processes that have shaped and reshaped the surface over billions of years. Understanding Venus's internal heat engine requires examining how planets cool, how magma forms and erupts, and why Venus's volcanic history differs so dramatically from Earth's. All rocky planets generate heat internally through radioactive decay. Uranium, thorium, and potassium, present in trace amounts in planetary interiors, undergo nuclear decay that releases energy. This heat accumulates over time unless it can escape to space. Additionally, residual heat from planetary formation, the primordial warmth from accretion and core formation, still radiates outward billions of years later. Venus, similar in size to Earth, contains comparable amounts of radioactive elements and retains substantial primordial heat. The challenge facing any planet is removing this heat. Earth accomplishes this efficiently through plate tectonics. Oceanic crust forms at mid-ocean ridges where mantle material rises and partially melts. This hot crust spreads away from the ridge, cools and eventually sinks back into the mantle at subduction zones. This conveyor belt system transports heat from the interior to the surface, where it radiates into space. Plate tectonics acts like a planetary cooling system, maintaining Earth's interior at temperatures where the mantle can convect and the core can generate a magnetic field. Venus lacks this mechanism. The planet's surface comprises a single rigid shell, a stagnant lid that doesn't break into moving plates. Without subduction to recycle crust and extract heat, Venus must cool through alternative means. The primary mechanism appears to be widespread volcanism, but the style and timing of this volcanism remain subjects of ongoing research. Volcanism on Venus occurs when mantle rock melts. This melting happens through decompression. When hot mantle rises toward the surface, the decreasing pressure allows it to cross the melting point and become partially molten. The resulting magma, being less dense than surrounding solid rock, rises further through cracks and conduits until it reaches the surface and erupts. On Venus, this process has operated on an enormous scale. The concentration of volcanic features on Venus exceeds anything seen elsewhere in the inner solar system. Mars has impressive volcanoes like Olympus Mons, but they're localized. Earth's volcanism concentrates at plate boundaries and hotspots. Venus, by contrast, shows volcanic features distributed across the entire planet. Vast lava plains cover most of the surface. Individual volcanoes number in the hundreds of thousands or millions. This volcanic productivity suggests vigorous mantle convection and extensive partial melting throughout Venus's history. The magmas erupted on Venus appear to be primarily basaltic, similar to the lavas that form Earth's oceanic crust and volcanic islands like Hawaii. Basaltic magma forms from partial melting of the mantle at depths of tens to hundreds of kilometers. The composition, rich in iron and magnesium, creates relatively fluid lavas that can flow great distances before solidifying. This fluidity explains the extensive lava plains and long flow channels observed on Venus. However, some evidence suggests more evolved magmas have also erupted. Pancake domes, with their viscous, piled-up appearance, might indicate more silica-rich compositions similar to andesite or even dacite. These compositions form through fractional crystallization, where minerals crystallize from basaltic magma and are removed, leaving behind magma enriched in silica. Alternatively, melting of previously altered crust could produce such compositions. The coronae that dot Venus's surface provide windows into the planet's heat loss mechanisms. These circular features, as mentioned earlier, likely form over mantle plumes, columns of hot material rising from deep within Venus. As a plume reaches the base of the lithosphere, it spreads laterally, creating a mushroom-shaped head. This uplift domes the surface, creating fractures through stretching. Magma from the partially molten plume head erupts through these fractures, building volcanic structures. As the plume cools and contracts, the central region subsides, forming the characteristic concentric fracture patterns. Mantle plumes represent an important heat transport mechanism on Venus. While not as efficient as plate tectonics at removing heat globally, plumes do extract heat from the deep mantle, including potentially from a hot thermal boundary layer at the core mantle interface. The large number of coronae on Venus, over 500 catalogued, suggests plume activity has been vigorous and widespread. The resurfacing hypothesis, proposing that Venus experienced a global or near-global volcanic event 300 to 500 million years ago, has profound implications for understanding the planet's thermal evolution. If correct, this event would have released enormous amounts of heat accumulated in Venus's interior. Prior to resurfacing, the stagnant lid would have trapped heat, causing mantle temperatures to rise. Eventually, perhaps when temperatures exceeded some critical threshold, the lithosphere became weak enough to founder or break apart, allowing massive volcanic eruptions to bury the old surface. This catastrophic resurfacing would have dramatically altered Venus's surface and atmosphere. Volcanic eruptions would have injected enormous quantities of gases, particularly sulfur dioxide and water vapor, into the atmosphere. Chemical reactions driven by these gases could have altered atmospheric composition and cloud properties. The release of internal heat would have temporarily increased Venus's heat flow to values exceeding Earth's, followed by a decline as the mantle cooled and the lithosphere thickened again. Some models suggest Venus might experience such resurfacing events episodically, perhaps every few 100 million years. Between events, the planet enters a stagnant lid phase where volcanism declines and heat accumulates. When conditions ripen, another resurfacing event occurs. This episodic overturn model contrasts with Earth's continuous plate tectonics and could explain why Venus's surface appears so uniformly young. Alternative models propose more continuous volcanism. Rather than catastrophic global events, Venus might experience ongoing eruptions at varying rates across the surface. In this view, the uniform crater density reflects an equilibrium between crater formation and volcanic obliteration. Volcanism continuously resurfaces portions of Venus, maintaining a relatively constant age. This model avoids requiring catastrophic events and aligns with observations suggesting some volcanic features might be quite young. Determining which model better describes Venus's volcanic history requires identifying active volcanism. Several lines of evidence suggest Venus might still be volcanically active today, though definitive proof remains elusive. The Venus Express mission detected temporal variations in sulfur dioxide abundance in the upper atmosphere. Sulfur dioxide is destroyed by sunlight over time, so maintaining concentrations requires replenishment from below. Volcanic eruptions could provide this source. Additionally, Venus Express observed transient bright spots in the near-infrared that could represent fresh lava flows still hot enough to glow even at wavelengths that penetrate the clouds. These hotspots appeared and faded over relatively short timescales, consistent with active eruptions. However, the observations remain difficult to interpret, and alternative explanations exist. Ground-based observations have also reported possible volcanic activity. Some researchers analysing archival Magellan radar data identified changes in surface brightness between different mapping cycles, suggesting fresh lava deposits. Others remain sceptical, pointing to calibration uncertainties and other factors that could produce apparent changes. The debate continues, with upcoming missions like VERITAS and ENVISION designed to definitively detect active volcanism if it occurs. The absence of plate tectonics on Venus raises questions about how the planet lost this potentially life-enabling process. Early in Venus's history, when surface temperatures were lower and water existed, conditions might have been suitable for plate tectonics. Liquid water weakens rocks and allows crust to bend and subduct. The presence of tesserae with complex deformation might represent remnants of an ancient mobile lid regime. As Venus heated and lost its water, the lithosphere stiffened. Without water to lubricate faults and reduce rock strength, subduction became impossible. The crust locked into a single rigid shell. From that point forward, Venus's thermal evolution followed a different path from Earth's, one characterized by stagnant lid convection and possibly catastrophic resurfacing. The volcanic history of Venus has shaped not just the surface, but also the atmosphere. Every eruption releases gases dissolved in the magma: carbon dioxide, water vapor, sulfur dioxide, and trace compounds. Over billions of years, volcanic outgassing has built up Venus's thick atmosphere. The continued presence of sulfur dioxide, a gas that breaks down over time, requires ongoing volcanic replenishment. linking the planet's interior activity to atmospheric composition. Interestingly, Venus's volcanic productivity might have declined over time. As the planet cools, the mantle temperature decreases, reducing the degree of partial melting. Less magma generation means less volcanism. If Venus experienced higher volcanic rates earlier in its history, the resurfacing event 500 million years ago might represent a transition to lower activity. Future observations will test this hypothesis. The fire within Venus continues burning, though we glimpse it only indirectly through surface features and atmospheric signals. The planet's interior remains hot, with a liquid core probably still present and a mantle convecting slowly beneath the stagnant lithosphere. Magma chambers lurk beneath volcanoes, possibly feeding eruptions even now. Venus, though lacking the tectonic vigour of Earth, is far from geologically dead. The fire burns on, hidden beneath clouds and crust, waiting for our next visit to reveal its secrets. Exploring Venus required courage, ingenuity, and a willingness to fail repeatedly. The planet's extreme environment destroyed more spacecraft than any other target in the solar system. Yet through persistence, scientists and engineers achieved remarkable successes, landing on another world and mapping its surface in exquisite detail. The voyages to Venus represent some of humanity's greatest achievements in planetary exploration. The space age began with Venus in the crosshairs. The planet's proximity to Earth and bright appearance made it an obvious target. In February 1961, the Soviet Union launched Venera 1, the first spacecraft intended to reach Venus. The probe carried scientific instruments to measure magnetic fields, cosmic rays, and solar wind, and was designed to release a capsule into Venus's atmosphere. However, contact was lost 7 days after launch, and Venera 1 sailed past Venus without returning data. The United States followed with Mariner 1 in July 1962, but a software error caused the rocket to veer off course, requiring destruction shortly after launch. This failure, caused by a missing hyphen in the guidance code, became legendary as one of the most expensive typographical errors in history. Mariner 2, launched a month later, succeeded spectacularly. In December 1962, it flew within 35,000 kilometers of Venus, returning data that confirmed the planet's high surface temperature and revealed the solar wind structure. The Soviets persisted. Venera 2, launched in 1965, failed just before its Venus encounter. Venera 3, launched days later, reached Venus in March 1966 and released a descent capsule, making it the first spacecraft to impact another planet. However, contact was lost before the capsule entered the atmosphere, so no data returned from Venus itself. These early failures highlighted the immense challenges of Venus exploration. Success came with Venera 4 in 1967. The spacecraft released a descent capsule that transmitted data during its fall through Venus's atmosphere for 93 minutes before going silent. The capsule measured temperature, pressure, and atmospheric composition, confirming carbon dioxide dominance and revealing much higher pressures than expected. Scientists initially thought the capsule reached the surface, but later analysis showed it succumbed to pressure and temperature at altitude around 25 kilometers above the surface. Venera 5 and 6 in 1969 improved on this achievement with strengthened capsules that survived deeper into the atmosphere before being crushed. The data revealed even higher surface pressures than previously estimated. These missions convinced Soviet engineers to redesign their landers for Venus's true hellish conditions. Venera 7 achieved a historic first on December 15, 1970, becoming the first spacecraft to successfully land on another planet and transmit from the surface. The capsule, heavily reinforced, survived the descent and transmitted for 23 minutes from the surface before succumbing to the heat. The achievement stunned the world and demonstrated that landing on Venus, while extremely difficult, was possible. Venera 8 followed in 1972, landing successfully and transmitting for 50 minutes. The lander measured light levels, finding that enough illumination reached the surface for photography despite the thick clouds. This discovery paved the way for future landers carrying cameras. The Venera 9 and 10 missions in 1975 were triumphs of engineering. Each consisted of an orbiter and a lander. Venera 9 landed on October 22, 1975, and transmitted the first photographs from the surface of another planet. The black and white images showed a rocky landscape with angular boulders, far clearer than most scientists expected. Venera 10 landed 3 days later and returned additional images from a different location, showing flatter terrain with rock slabs. Both landers survived approximately 1 hour on the surface. These successes continued with Venera 11 and 12 in 1978, though neither camera functioned, denying us additional surface images. Venera 13 and 14, landing in 1982, restored photography and added colour. Venera 13 returned the first colour images from Venus's surface, revealing an orange-lit landscape of flat rocks under a hazy sky. The lander survived for 127 minutes, the longest survival time achieved on Venus. It also analysed soil samples using an X-ray fluorescent spectrometer, determining chemical composition. Venera 15 and 16, arriving in 1983, carried no landers, but instead orbited Venus with synthetic aperture radar systems. These missions mapped the northern hemisphere at resolutions of 1 to 2 kilometers, revealing volcanoes, mountains, and bizarre features that would later be confirmed and extended by Magellan. The United States launched Pioneer Venus in 1978, consisting of an orbiter and a multiprobe mission. The orbiter carried a radar altimeter that created the first global topographic map of Venus, operating until 1992. The multiprobe mission released 4 atmospheric probes that descended through different regions, measuring atmospheric structure, composition, and dynamics. One probe survived impact and transmitted briefly from the surface, though it carried no surface instruments. NASA's Magellan mission, launched in 1989, revolutionized our understanding of Venus's surface. Using synthetic aperture radar, Magellan mapped 98% of the planet at resolutions down to 120 meters. Over 4 years of operation, the spacecraft revealed Venus's volcanic nature, identified thousands of geological features, and collected topographic data with unprecedented accuracy. Magellan's radar penetrated the clouds, finally unveiling the surface in comprehensive detail. The mission ended dramatically. As Magellan's orbit decayed in October 1994, mission controllers conducted aerobraking experiments, dipping the spacecraft into Venus's upper atmosphere to test technologies for future missions. Finally, on October 12, 1994, Magellan plunged into the atmosphere and burned up, ending one of NASA's most successful planetary missions. Europe entered Venus exploration with Venus Express, which orbited the planet from 2006 to 2014. The mission focused on atmospheric science, studying cloud structure, atmospheric dynamics, and searching for signs of volcanic activity. Venus Express provided the first detailed observations of the South Polar Vortex, detected possible volcanic activity through sulfur dioxide variations and infrared hotspots, and characterized the interaction between the solar wind and Venus's ionosphere. Japan's Akatsuki spacecraft, launched in 2010, initially failed to enter orbit around Venus in December 2010 due to engine problems. The spacecraft spent 5 years in solar orbit before attempting orbit insertion again in December 2015, succeeding on its second try. Akatsuki has studied atmospheric dynamics, particularly the mysterious ultraviolet markings in the clouds and the mechanics of superrotation. The mission continues to operate, providing valuable long-term observations of Venus's atmosphere. The landers that reached Venus's surface experienced conditions almost beyond comprehension. Surface temperature of 464 degrees Celsius melts lead. Atmospheric pressure of 92 bars equals the pressure at 900 meters depth in Earth's ocean. Sulfuric acid vapor corrodes most materials. The combination creates an environment more hostile than any deep-sea hydrothermal vent or volcanic crater on Earth. Soviet engineers designed the Venera landers as pressure vessels, thick-walled metal spheres that could withstand the crushing environment. Internal temperatures were maintained below 50 degrees Celsius through insulation and pre-cooling. Electronics were designed to function briefly at elevated temperatures. Cameras used panoramic scanning mechanisms that minimized complexity. The landers were marvels of engineering, each representing years of design, testing, and refinement. The images returned from the surface show landscapes of volcanic rock under orange skies. Venera 9's landing site displayed angular rocks suggesting relatively young terrain that hadn't undergone extensive weathering. Venera 10's site showed flatter, older-looking terrain with more eroded rocks. Venera 13 and 14's colour images revealed the true appearance of Venus's surface, with the orange coloration caused by scattering and absorption of light by the thick atmosphere above. One remarkable aspect of these missions was their scientific return, given the limited operating time. Venera 13, in its 127 minutes on the surface, measured atmospheric composition, analysed soil chemistry, recorded sound levels, and took multiple photographs. The landers transmitted data to their orbiter companions, which relayed it to Earth. This architecture allowed the delicate landers to avoid carrying large antennas and transmitters, simplifying their design. The Soviet Vega program in 1985 combined Venus exploration with encounters with Halley's Comet. Vega 1 and 2 each released a lander and a balloon probe into Venus's atmosphere before continuing to comet intercepts. The landers performed measurements similar to earlier Veneras. The balloon probes, however, represented something new. Each balloon, filled with helium, floated in Venus's atmosphere at around 50 kilometers altitude for approximately 2 Earth days, carried along by the super-rotating winds. These balloons measured atmospheric temperature, pressure, density, and vertical winds while drifting thousands of kilometers around the planet. The Vega balloons provided the first direct measurements of atmospheric dynamics at cloud level and demonstrated the feasibility of aerial exploration. Unfortunately, no subsequent missions have repeated this approach, though future proposals include various aerial platforms. International cooperation characterized later missions. Venus Express, though built by the European Space Agency, included instruments from several nations and relied on NASA's Deep Space Network for communication support. Similarly, Akatsuki receives tracking support from international facilities. This cooperation reflects the global nature of planetary science and the shared interest in understanding Earth's sister planet. Not all missions succeeded. The Soviet Union launched several additional Venus missions that failed at various stages. Mars 96, though primarily targeted at Mars, intended to drop penetrators into Venus's atmosphere, but failed to escape Earth orbit. NASA has proposed numerous Venus missions that were not selected for development, including everything from sample return attempts to long-lived surface stations. The challenges of Venus exploration continue to spur innovation. Future landers might use advanced materials like silicon carbide electronics that can operate at high temperatures, eliminating the need for pressure vessels and cooling. Proposed aerial platforms range from solar-powered aircraft to robotic rovers suspended from balloons. Sample return missions would require solving the extraordinary challenge of launching from Venus's surface through its thick atmosphere. The voyages to Venus have yielded enormous scientific rewards. We've measured the atmosphere from top to bottom. We've mapped the surface in detail. We've analysed rocks and captured images from another world. Yet mysteries remain. We still don't know if Venus is volcanically active today. We haven't explored beneath the surface. We haven't determined definitively whether life could exist in the clouds. The journey to understand Venus continues, with new missions on the horizon promising to answer questions raised by decades of exploration. Before spacecraft and radar revealed Venus's true nature, humanity knew the planet only as a brilliant light in the sky, brighter than any star, appearing in the west after sunset or in the east before dawn. Venus commanded attention from the earliest civilizations. Cultures around the world wove Venus into their mythologies, making the planet a goddess, a warrior, a herald, a symbol of beauty and destruction. The ancient Sumerians, among the earliest literate civilizations, knew Venus as Inanna, the goddess of love, fertility, and warfare. This dual nature, combining aspects we might consider contradictory, made Inanna one of the most complex deities in the Sumerian pantheon. She was patron of the city of Uruk, and myths described her descent into the underworld, her conflicts with other gods, and her passionate nature. The Babylonians later identified Venus with Ishtar, inheriting and expanding Inanna's myths. In Babylonian astronomy, Venus was called Nindarana or Dilbat. The planet's movements were carefully recorded on clay tablets, with scribes noting its appearances and disappearances over years and decades. These observations, driven partly by astrological beliefs but conducted with scientific rigour, created one of the longest continuous records of astronomical observation in human history. The Babylonians recognized that the morning star and evening star were the same object, a realization not all ancient cultures achieved. Ancient Egyptians knew Venus by multiple names depending on its position. Tiamutiri meant the morning star, while Waiti meant the evening star. The Egyptians eventually realized these were the same celestial body. Venus played a less central role in Egyptian mythology than in Mesopotamian cultures, but was associated with various deities at different periods, sometimes connected with Hathor or Isis. Greek mythology gave us the name we use today. The Greeks called the evening appearance Hesperos and the morning appearance Phosphoros before recognizing their identity. The planet became associated with Aphrodite, the goddess of love and beauty born from sea foam. The Romans later identified Aphrodite with Venus, and this Roman name became standard in Western astronomy. Venus's mythology in Greco-Roman culture emphasized beauty and desire. Aphrodite Venus was the most physically beautiful of the goddesses, desired by gods and mortals alike. Her birth from the sea, her marriage to the craftsman god Hephaestus Vulcan, her affairs with Ares Mars the war god, and her role in the Trojan War all form central myths of classical antiquity. The planet's brightness seemed fitting for such a goddess. The Romans associated Venus with gardens, vineyards, and the coming of spring. The month of April was sacred to Venus, and festivals like the Veneralia and Venalia celebrated the goddess and marked important moments in the agricultural year. This connection to fertility and growth reflects the planet's role as a herald of seasonal change, rising before the sun in spring or following the sun in autumn. Mesoamerican cultures developed sophisticated astronomical systems that tracked Venus with remarkable precision. The Maya knew Venus as Chakek, the great star, and observed its cycles meticulously. The Dresden Codex, a pre-Columbian Maya manuscript, contains tables predicting Venus's appearances over centuries. The Maya recognized that Venus's synodic period, the time between successive appearances in the same part of the sky, averages 584 days, close to the modern value of 583.92 days. For the Maya, Venus had ominous associations. The planet's first appearance as a morning star, rising helically after its conjunction with the Sun, was considered especially dangerous. Warfare was often timed to coincide with this appearance. Kings would consult the Venus tables before launching campaigns, believing the planet's malevolent influence could be directed at enemies. The god Kukulkan, the feathered serpent, had associations with Venus in some contexts. The Aztecs knew Venus as Tlahuizcalpantecutli, Lord of the Dawn, when appearing in the morning. The planet was considered an aspect of Quetzalcoatl, the feathered serpent deity central to Aztec religion. Myths describe Quetzalcoatl's self-immolation and transformation into Venus. Like the Maya, the Aztecs tracked Venus's movements carefully and attributed both favourable and unfavourable influences to different phases of its cycle. Indigenous peoples across the Americas observed Venus and incorporated it into their traditions. Plains tribes recognized the morning star and evening star's identity. Some tribes associated Venus with the trickster figure, appropriate given the planet's changing behaviour. Pacific Northwest groups included Venus in their origin stories and navigational knowledge. Each culture interpreted the brilliant light according to their worldview, but all recognized Venus's uniqueness. In ancient China, Venus was called Tai Bai, the Great White, or Jinxing, the metal star in the five-element system where it represented metal. Chinese astronomers tracked Venus's movements as part of their court responsibilities, believing celestial events portended earthly changes. Venus's appearances were connected to warfare and strategy, with military theorists sometimes timing campaigns according to the planet's position. Hindu astronomy knew Venus as Shukra, associated with the guru of the Asuras in Hindu mythology. Shukra was considered a benefic planet in Vedic astrology, influencing matters of love, beauty, art and luxury. The planet's movement through the zodiac was carefully tracked, and its position at a person's birth was thought to influence their character and fortune. Islamic astronomers inherited and expanded upon Greek and Indian astronomical knowledge. They made precise observations of Venus's movements, improving orbital parameters and creating detailed tables predicting its position. These observations, conducted from observatories across the Islamic world, contributed to the development of mathematical astronomy and were later transmitted to medieval Europe. The recognition that Venus has phases like the Moon came in 1610 when Galileo observed the planet through his newly improved telescope. He saw Venus go through a complete cycle from crescent to gibbous to nearly full and back, providing strong evidence for the Copernican heliocentric model of the solar system. In the Ptolemaic geocentric model, Venus should always appear as a crescent. The observed phases proved Venus orbits the Sun, not Earth. This discovery sparked controversy and contributed to Galileo's conflict with religious authorities. The phases of Venus couldn't be explained away or reinterpreted to fit the old model. They provided clear visual proof that at least some celestial bodies orbited the Sun. Combined with Galileo's observations of Jupiter's moons, the evidence for a sun-centered system became overwhelming to those willing to examine it objectively. Throughout the modern era, Venus has maintained its cultural significance, though our understanding has transformed from mythology to science. The planet appears frequently in literature, from science fiction stories imagining Venusian jungles to philosophical works contemplating humanity's place in the cosmos. Venus has inspired art, music, and poetry, its appearance in the twilight sky still capable of stirring emotion even in an age of space exploration. The names given to Venus's features continue this mythological tradition. The International Astronomical Union, responsible for naming planetary features, decided that Venusian features would be named after goddesses and famous women from various cultures. Highland regions bear names of love goddesses, Ishtar Terra, Aphrodite Terra, Lada Terra. Individual features honour women from history and mythology. Craters commemorate women artists, writers, and scientists, while mountains, valleys, and coronae bear names from world mythology. This naming convention connects our modern scientific understanding to the ancient traditions that first recognised Venus's special place in the heavens. Maxwell Montes, the highest mountain on Venus, honours James Clerk Maxwell, whose equations unified electricity and magnetism and predicted electromagnetic waves. The choice honours his contribution to physics while maintaining the naming pattern, as mountains typically bear names of scientists associated with Venus research. Venus's role as morning and evening star has entered common language and culture. References to the evening star appear throughout literature and song, usually evoking romance, beauty, or wistfulness. The planet's brilliant appearance has inspired countless observers to pause in their daily routines and contemplate the sky, connecting modern humanity to ancestors who watched the same light thousands of years ago. In astrology, Venus continues to represent love, beauty, harmony, and material pleasure. While modern science rejects astrological determinism, the symbolic associations reflect ancient observations of the planet's behaviour. Its brightness suggesting attractiveness, its regular cycles suggesting reliability in relationships, its association with the goddess of love carrying forward into interpretative frameworks. Whether one accepts astrological claims or not, Venus's cultural presence remains strong. The transformation in how we understand Venus, from goddess to planet to world of sulfuric clouds and volcanic plains, represents the evolution of human knowledge. Yet something of the original wonder remains. When Venus shines in the western sky after sunset, bright enough to cast shadows on moonless nights, it's easy to understand why ancient peoples saw divinity in that light. The scientific reality of a hellish planet with runaway greenhouse warming doesn't diminish the beauty of that brilliant point above the horizon. If anything, knowing what Venus truly is makes its appearance more poignant. A reminder that beauty can conceal extremes, and that understanding requires looking beyond surface appearances. Despite decades of observation and exploration, Venus guards many secrets. Some mysteries stem from technological limitations, our inability to sustain long-term observations of the surface or atmosphere. Others arise from incomplete theories, where our understanding of planetary processes remains insufficient to explain what we observe. And some questions might have surprising answers that challenge our assumptions about life, climate, and planetary evolution. Perhaps the most controversial recent mystery concerns phosphine. In September 2020, a team of astronomers announced the detection of phosphine gas in Venus's atmosphere, observed using the James Clerk Maxwell telescope and the Atacama Large Millimeter Array. Phosphine, a molecule consisting of one phosphorus atom bonded to 3 hydrogen atoms, is significant because on Earth it's produced primarily by anaerobic bacteria or industrial processes. Its detection on Venus, if confirmed, could indicate biological activity or unknown chemistry. The initial detection reported phosphine at concentrations around 20 parts per billion, at altitudes between 50 and 60 kilometers, within Venus's cloud layers. The researchers carefully considered possible abiotic formation mechanisms: lightning, volcanic activity, meteorite delivery, and various chemical reactions. None of these processes could account for the observed abundance. The team cautiously suggested that either unknown chemistry was producing phosphine or the detection might indicate life. The announcement sparked intense debate. Some researchers questioned the data analysis, suggesting that the spectral feature attributed to phosphine might actually be sulfur dioxide, which absorbs at similar wavelengths. Reanalysis using different techniques yielded conflicting results, with some confirming the detection and others finding no evidence for phosphine. The situation became contentious, with various teams publishing contradictory papers. Additional observations attempted to resolve the dispute. Some ground-based telescopes detected possible phosphine signals, while others found nothing. Data from older missions were re-examined with ambiguous results. The situation remains unresolved. As of late 2024, future missions carrying instruments specifically designed to detect phosphine will hopefully settle the question definitively. If phosphine exists on Venus, understanding its source becomes paramount. If it doesn't, the controversy will still have spurred scientific discussion about Venus's chemistry and the challenges of remote sensing. The possibility of life in Venus's clouds, while speculative, deserves serious consideration. The cloud layer at 50 to 60 kilometers altitude offers conditions far more benign than the surface. Temperatures range from 0 to 50 degrees Celsius, pressures approximate Earth's surface, and liquid water droplets could exist. These conditions, while not comfortable, fall within the range tolerated by extremophile organisms on Earth. However, the clouds are made of concentrated sulfuric acid, typically around 80 to 90% concentration. This extreme acidity would destroy most terrestrial organisms. Additionally, water activity, the amount of water available for biological processes, is extremely low in sulfuric acid. Life requires water, and Venus's clouds seem far too dry. Any organisms would need remarkable adaptations to survive. Proposed scenarios for Venusian life suggest microorganisms might exist within liquid droplets, protected from the surrounding acid. Or perhaps they coat themselves in protective shells of sulfur or other materials. They might metabolize sulfur compounds using the abundant sulfur dioxide and sulfuric acid in their environment. They could reproduce through spores that remain dormant during harsh conditions and become active in favorable microenvironments. One intriguing possibility suggests that if life exists on Venus today, it might be descended from organisms that evolved when Venus was more hospitable. As the planet heated and the oceans evaporated, any life would have been forced to adapt or die. Some microorganisms might have retreated to the clouds, the last refuge where temperatures and pressures allowed liquid water. Over millions of years, these organisms would have adapted to increasingly acidic and dry conditions, eventually reaching the extremophile forms that might persist today. This scenario requires several assumptions. Life must have arisen on early Venus, something we have no evidence for. That life must have been capable of existing in atmospheric suspension, unlike most terrestrial life, which requires surfaces. It must have survived the transition from a habitable surface to a hellscape, finding refuge in the clouds. And it must continue to persist in conditions that seem fundamentally inhospitable. Each step seems unlikely, but the cumulative possibility, while small, isn't zero. Another major mystery concerns volcanic activity. Is Venus volcanically active today? The planet clearly has abundant volcanic features, but their ages remain uncertain. The crater statistics suggest most of the surface dates to between 300 and 500 million years ago. But this doesn't preclude more recent volcanism in localized areas. Several lines of evidence hint at ongoing activity. Venus Express detected variations in sulfur dioxide concentration in the upper atmosphere. Sulfur dioxide has a lifetime of only a few years before photochemical reactions destroy it, so maintaining observed levels requires continuous replenishment. Volcanic eruptions could provide this source. However, alternative explanations exist. Meteorite impacts could vaporize sulfate-bearing rocks, or atmospheric circulation might bring sulfur dioxide from lower altitudes where it's stable. Infrared observations from Venus Express identified thermal anomalies on the surface, spots apparently hotter than their surroundings. Some researchers interpret these as fresh lava flows that haven't cooled to equilibrium temperatures. Others suggest the observations reflect measurement uncertainties or unusual surface compositions rather than active volcanism. The evidence remains ambiguous. Analysis of Magellan radar data identified possible changes in surface brightness between different mapping cycles. These changes, concentrated in certain volcanic regions, might indicate fresh lava deposits. However, the radar system's calibration varied between orbits, making it difficult to distinguish real surface changes from instrumental effects. The question requires new radar observations with carefully controlled calibration. Seismology could definitively answer the volcanism question. Earthquakes on Earth are easy to detect with seismometers, and volcanic eruptions create characteristic seismic signals. A seismometer on Venus would detect quakes from active tectonism or volcanism. Unfortunately, no seismometer has yet operated on Venus's surface long enough to gather useful data. Future landers carrying seismic instruments could finally resolve whether Venus's interior actively convulses or lies mostly dormant. The mechanism of Venus's superrotation remains incompletely understood. While general circulation models can reproduce some aspects of the high-altitude winds, the detailed physics driving winds 60 times faster than the planet's rotation continue to puzzle atmospheric scientists. The process involves complex interactions between solar heating, atmospheric waves, and thermal tides, but precisely how these factors combine to produce superrotation isn't fully explained. Recent research suggests that thermal tides, atmospheric oscillations driven by day-night temperature contrasts, might play a crucial role. Even though Venus rotates slowly, the Sun heats the atmosphere on the day side while the night side cools. This creates pressure waves that propagate through the atmosphere. If these waves interact with the mean circulation in specific ways, they could deposit angular momentum, accelerating the winds. However, the models remain incomplete, and observations don't yet fully constrain the theories. The loss of Venus's magnetic field poses another puzzle. Did Venus once have a magnetic field similar to Earth's? If so, when and why did it shut down? The planet's size and presumed iron core suggest it should be capable of generating a dynamo. Earth's magnetic field has reversed polarity many times, but has never completely disappeared. What happened to Venus? Several theories exist. The loss of water from Venus's mantle could have altered convection patterns in the core, shutting down the dynamo. The extremely slow rotation might provide insufficient Coriolis force to organize fluid motions into a dynamo. Venus might have experienced a catastrophic impact that disrupted its rotation and magnetic field. Or the core might have a different composition or thermal structure than Earth's, preventing dynamo action. Evidence for an ancient magnetic field would come from magnetized rocks, but the surface's relative youth erases any record of ancient magnetic fields. Even if older rocks exist, Venus's high surface temperature approaches the Curie point for many magnetic minerals, above which they lose their magnetization. Finding proof of ancient magnetism on Venus would require either excavating deep below the surface or discovering exceptionally old, cool rocks in highland regions. The question of water on early Venus remains hotly debated. How much water did Venus have? Did oceans exist? For how long? The deuterium to hydrogen ratio suggests enormous water loss, but the initial inventory remains uncertain. Some researchers argue Venus started with water comparable to Earth's oceans. Others propose Venus always had less water, perhaps due to its formation location in the protoplanetary disk. The timing of water loss directly affects the possibility of early habitability. If Venus lost its water within the first few 100 million years, it would have been hostile throughout most of solar system history. If Venus maintained moderate temperatures and liquid water for 1 billion years or more, it would have had a substantial habitability window during which life might have arisen. Answering this question requires better understanding of atmospheric escape processes, improved models of early solar system conditions, and possibly even sample return missions. Analyzing noble gas isotope ratios in Venus's atmosphere could constrain atmospheric loss rates and help reconstruct the planet's volatile history. Future missions designed to study atmospheric chemistry in detail will contribute to resolving this debate. The nature of tesserae terrain raises questions about Venus's early geology. Do these intensely deformed regions represent ancient continents, perhaps formed through processes similar to Earth's plate tectonics? Or did they form through entirely different mechanisms unique to Venus? The complex deformation patterns suggest multiple episodes of compression, extension, and shearing, but deciphering the sequence of events from radar images alone proves difficult. Some researchers propose that tesserae formed through crustal overturn, where dense cold lithosphere foundered into the mantle and lighter material rose to replace it. Others suggest tesserae represent impact basin ejecta or volcanic constructs that subsequently experienced intense deformation. The debate highlights our limited understanding of Venus's tectonic evolution and the challenge of interpreting geological history without ground truth. The presence of certain minerals on Venus remains speculative. Do economically valuable concentrations of metals exist? The surface's basaltic composition suggests the presence of iron, titanium, and other elements, but concentrations and accessibility remain unknown. Understanding Venus's mineralogy requires additional surface missions with sophisticated analytical instruments or, ultimately, sample return. Climate scientists debate Venus's relevance as an analogue for Earth's future. As Earth warms due to increasing carbon dioxide from human activities, could it eventually experience a runaway greenhouse effect like Venus? Most climate models suggest not, at least not from anthropogenic emissions alone. Earth's greater distance from the Sun and the presence of oceans provide stabilizing feedbacks that Venus lacked. However, understanding the threshold for runaway greenhouse effects remains crucial for assessing long-term climate risks. Venus thus serves as both a laboratory for studying runaway climate change and a cautionary example of what can go wrong. The planet demonstrates that Earth-like worlds can become uninhabitable through atmospheric processes. It shows that initial conditions and distance from the star matter enormously in determining a planet's fate, and it reminds us that planetary climates can undergo irreversible transitions, crossing thresholds beyond which return to earlier states becomes impossible. Venus's mysteries demand new investigations. After decades of limited exploration, the planetary science community has renewed focus on Venus with multiple missions in development. These upcoming ventures promise to answer long-standing questions and undoubtedly reveal new puzzles, continuing humanity's quest to understand our enigmatic neighbour. NASA has selected 2 Venus missions for its Discovery program, both scheduled for launch in the late 2020s or early 2030s. DAVINCI, short for Deep Atmosphere. Venus investigation of noble gases, chemistry and imaging will send a probe through Venus's atmosphere, making detailed measurements from the cloud tops to the surface. The mission focuses on atmospheric composition, seeking to understand Venus's climate history and the current state of the atmosphere. DAVINCI's descent probe will carry a mass spectrometer to measure atmospheric composition with unprecedented precision. This instrument will detect trace gases, isotope ratios, and vertical variations in composition throughout the descent. Of particular interest are noble gas measurements. The abundances and isotope ratios of neon, argon, krypton, and xenon can reveal whether Venus's atmosphere formed primarily from volcanic outgassing or received significant contributions from cometary impacts. The probe will also carry a Venus-tunable laser spectrometer to measure water vapor and sulfur compounds at various altitudes. Understanding water distribution provides clues about circulation patterns and cloud formation. Sulfur compound measurements address volcanic activity, as active volcanism should produce detectable sulfur dioxide variations. Perhaps most excitingly, DAVINCI includes a camera system called VISOR that will take high-resolution images during the final descent through the lowest atmosphere. These images will reveal surface geology at scales of tens of meters, far better than Magellan's radar resolution. The target landing site includes tessera terrain, allowing detailed examination of these ancient, deformed regions. The descent probe will survive on the surface for at least 17 minutes, though possibly longer if systems endure. During surface operations, instruments will continue measuring atmospheric composition just above the ground, providing ground truth for interpreting orbital and aerial observations. The probe might also detect sounds, including potential thunder if lightning occurs, or seismic rumbles if volcanic or tectonic activity happens nearby. DAVINCI also includes a flyby component. The carrier spacecraft will make 2 close passes of Venus before releasing the descent probe, using cameras to image the night side in infrared wavelengths. These observations will search for thermal emission from fresh lava flows or volcanic vents, potentially confirming active volcanism. VERITAS, the Venus Emissivity, Radio Science, INSAR, Topography, and Spectroscopy mission will orbit Venus and conduct comprehensive surface mapping. The mission's primary goal is to understand Venus's geological history through detailed surface characterization. VERITAS will carry 3 main instruments that work together to paint a complete picture of Venus's geology. The Venus Interferometric Synthetic Aperture. Radar will map the entire planet at resolutions of 15 to 30 meters, far surpassing Magellan's resolution. This radar will create topographic maps with vertical precision of 5 to 10 meters and surface images showing features as small as boulders. The improved resolution will reveal small-scale geological structures, allowing scientists to understand volcanic features, tectonic deformation, and impact processes in unprecedented detail. The Venus Emissivity Mapper will observe surface thermal emission in multiple infrared wavelengths. Different minerals emit infrared radiation at different intensities depending on temperature and composition. By mapping these emissivity variations, VERITAS will produce global compositional maps showing where different rock types exist. This will help identify evolved rocks similar to granite, which would suggest past water-driven processes versus more primitive basaltic compositions. The emissivity mapper will also search for active volcanism. Fresh lava flows, still hot from recent eruption, would show distinct thermal signatures. Comparing observations taken months or years apart will reveal any changes, definitively determining whether Venus experiences ongoing volcanic activity. If active volcanoes are found, their locations and eruption styles will constrain models of Venus's internal dynamics. VERITAS will also conduct radio science experiments using its communication system. By precisely tracking the spacecraft's motion as it orbits Venus, scientists can map subtle variations in the planet's gravity field. These variations reflect density differences in the crust and mantle, revealing internal structure. Gravity measurements combined with topography help determine whether highland regions have thick crustal roots, similar to continental masses on Earth, or represent surface features without deep compensation. Repeated gravity measurements over time could detect changes indicating mass redistribution within Venus. If large magma chambers fill or drain during volcanic activity, or if mantle convection patterns shift, the gravity field would change detectably. Such measurements would probe Venus's interior dynamics in ways never before possible. The European Space Agency's ENVISION mission, selected for launch in the early 2030s, will provide complementary observations to VERITAS. ENVISION will carry radar systems to map the surface and subsurface, a spectrometer to study surface composition and atmospheric trace gases, and instruments to characterize the atmosphere and ionosphere. The mission will focus on geological activity, searching for signs of active volcanism and studying regions with evidence of recent activity. ENVISION's subsurface radar will probe beneath Venus's surface, searching for layered structures indicating sedimentary deposits or volcanic stratigraphy. On Earth, ground-penetrating radar reveals buried structures, faults, and variations in rock properties with depth. On Venus, subsurface radar could identify buried impact craters, lava flow sequences, or possibly even ancient shorelines if Venus once had oceans. The spectrometer will make extremely detailed compositional maps, identifying specific minerals on the surface. This data will help determine whether highlands contain evolved rocks like granite, which form in water-rich environments. Finding granite would strongly suggest early Venus had liquid water and possibly plate tectonics. The instrument will also search for variations in surface weathering, which might reveal regional differences in atmospheric chemistry or temperature. Russia's space agency Roscosmos has discussed Venera D, a proposed mission combining an orbiter, a lander, and potentially aerial platforms. The lander would operate for extended periods, possibly hours, using advanced high-temperature electronics based on silicon carbide semiconductors. These materials remain functional at Venus's surface temperature, eliminating the need for cooling systems and allowing longer duration missions. Venera D's science goals include studying surface composition and morphology, searching for seismic activity, and characterizing atmospheric dynamics. The mission would carry ground-penetrating radar to probe below the surface and possibly a small rover to explore the landing site. While Venera D's status remains uncertain due to budget constraints and international cooperation questions, the mission represents Russia's continued interest in Venus exploration. India's space agency ISRO has proposed Shukrayan-1, an orbital mission to study Venus's atmosphere, surface, and interaction with the solar wind. The mission would carry radar, spectrometers, and atmospheric instruments, focusing on understanding Venus's climate and geological history. ISRO's successful missions to the Moon and Mars demonstrate their capability, and Venus represents a natural next target. Several private organizations and smaller space agencies have proposed Venus missions, ranging from CubeSats to balloon platforms. While these missions face funding and technical challenges, they reflect growing international interest in Venus exploration. The planet's scientific importance and relative accessibility compared to more distant targets make it attractive for diverse exploration strategies. One particularly exciting concept involves aerial platforms that could explore Venus's cloud layers for extended periods. Solar-powered aircraft could fly at altitudes where temperatures and pressures remain moderate, conducting atmospheric chemistry measurements and searching for signs of life. Balloon platforms could drift with the super-rotating winds, sampling clouds across multiple locations. These aerial missions could directly address the phosphine question by collecting cloud samples and analysing them with sensitive instruments. They could characterise the mysterious ultraviolet absorber in the clouds, determining its composition and distribution. And they could study atmospheric dynamics, measuring wind speeds, temperature profiles, and cloud particle properties in situ rather than remotely. Sample return remains the ultimate goal for many scientists. Bringing Venus material back to Earth would allow analysis with laboratory instruments far more sophisticated than anything flown on spacecraft. Samples could be dated using radiometric techniques, precisely determining the ages of different geological units. Mineralogical analysis would reveal formation conditions and any aqueous alteration. Isotopic measurements could constrain Venus's volatile history and atmospheric escape rates. However, Venus sample return poses extraordinary challenges. The spacecraft must survive the descent, collect samples, launch from the surface through Venus's thick atmosphere, rendezvous with an orbiter, and return to Earth. Each step pushes engineering capabilities. Surface sample collection must occur quickly before systems fail in the extreme heat. Launch from Venus requires a rocket capable of reaching orbit from 92 atmospheres of pressure. The technology required exceeds current capabilities, but doesn't violate physical laws, suggesting eventual success with sufficient development. Crewed missions to Venus orbit have been proposed, though surface visits seem unlikely given the hostile conditions. Astronauts could teleoperate landers and rovers in real time, eliminating communication delays that hamper robotic missions. They could respond to unexpected discoveries, redirecting exploration based on findings. And orbital missions could serve as proving grounds for deep space human exploration technologies. Venus exploration also benefits from comparative planetology studies. Understanding why Venus and Earth diverged helps us understand what makes planets habitable. As we discover exoplanets around other stars, many fall in the category of supervenuses, rocky planets close to their stars where runaway greenhouse effects seem likely. Understanding Venus helps us interpret observations of these distant worlds and assess their habitability potential. The coming decades promise remarkable discoveries. We will map Venus's surface at unprecedented resolution, revealing geological processes in exquisite detail. We will measure atmospheric composition precisely, constraining theories of climate evolution and atmospheric chemistry. We might detect active volcanism, confirming that Venus remains geologically vital. We could even find evidence of life, however unlikely, revolutionizing our understanding of biology's cosmic distribution. Venus awaits our return. After decades of neglect, the planet will once again receive the attention its mysteries deserve. Each new mission will write another chapter in the story of Venus, revealing details we can scarcely imagine. And perhaps eventually, humans will stand in orbit around Venus, gazing down at the cloud-shrouded world that has captivated humanity since our ancestors first noticed that brilliant star in the twilight sky. Venus teaches. Its story, written in atmosphere and rock across billions of years, offers lessons relevant to understanding our own planet and the universe beyond. The most obvious lesson concerns climate. Venus demonstrates that planetary climates can undergo catastrophic transitions, crossing thresholds beyond which stabilizing feedbacks fail and runaway processes take over. The runaway greenhouse effect transformed a potentially habitable world into an inferno, showing that small initial differences can compound into vast divergences over time. Earth, blessed with greater distance from the sun and abundant liquid water, has maintained relatively stable climates over billions of years. But stability isn't guaranteed. Venus reminds us that planetary climates exist in delicate balance. Push too hard in one direction, and feedbacks that normally maintain equilibrium might instead amplify changes, driving the system into a new state far removed from the original. This cautionary tale becomes especially relevant as humanity alters Earth's atmosphere through fossil fuel combustion, deforestation, and agriculture. While Earth isn't in immediate danger of a Venus-like runaway greenhouse, the principle remains. Atmospheres can change, sometimes rapidly, and those changes can be irreversible on human timescales. Understanding Venus helps climate scientists identify potential tipping points in Earth's climate system and assess risks associated with various levels of greenhouse gas concentration. Venus also teaches about the importance of water. This simple molecule, so abundant on Earth that we take it for granted, plays crucial roles in planetary habitability. Water enables plate tectonics by weakening rocks and allowing subduction. It regulates climate through the hydrological cycle of evaporation, precipitation, and runoff. It dissolves carbon dioxide, locking it away in carbonate rocks and preventing atmospheric buildup. And it provides the medium in which life, at least terrestrial life, exists. Venus's loss of water cascaded into multiple consequences: the end of plate tectonics, the accumulation of atmospheric carbon dioxide, rising temperatures, and ultimately a lifeless wasteland. Water isn't just necessary for life, it's integral to maintaining the geological and atmospheric processes that keep a planet habitable. Earth's water inventory, delivered by asteroids and comets early in solar system history, represents one of our most precious resources, not just for human use, but for the planet's long-term habitability. The absence of plate tectonics on Venus highlights how unusual Earth's geological activity might be. Of all the rocky bodies in the solar system, only Earth exhibits active plate tectonics today. Mars and the Moon show evidence of ancient tectonic activity, but have been geologically quiet for billions of years. Venus might have had plate tectonics early on, but transitioned to a stagnant lid regime. Mercury appears to have always had a static crust. Earth stands alone as a tectonically active world. This raises profound questions about planetary habitability. Is plate tectonics necessary for long-term habitability? It certainly helps on Earth by recycling carbon, rejuvenating the surface, and driving chemical cycles that support life. But must all habitable worlds have plate tectonics? Or could alternative geological processes, perhaps like Venus's episodic resurfacing or distributed volcanism, maintain habitability on other planets? As we search for potentially habitable exoplanets, understanding the role of tectonics becomes crucial. If plate tectonics is necessary, we should prioritize planets likely to have active surface recycling, the right size, composition, and thermal state. If plate tectonics is merely helpful, but not required, the number of potentially habitable worlds increases dramatically. Venus, by showing us a world without plate tectonics, helps frame these questions. Venus's atmospheric evolution demonstrates the importance of magnetic fields for protecting atmospheres. Earth's magnetic field deflects solar wind, preventing atmospheric stripping. Mars lost much of its atmosphere after its magnetic field shut down. Venus, lacking magnetic protection, has lost substantial atmosphere over billions of years, though its initial atmospheric mass was large enough to withstand ongoing losses. For smaller planets or moons with thinner atmospheres, magnetic protection might determine whether atmospheres persist or evaporate away. The potential for life in Venus's clouds, while speculative, expands our thinking about habitable environments. Habitability traditionally focuses on surfaces with liquid water, but if life could exist in atmospheric clouds, suspended and floating, the concept of habitable zones around stars would broaden significantly. Even planets with hellish surfaces might maintain cloud layer habitats where conditions remain moderate. This possibility increases the potential for life in the universe and suggests we should look beyond just surface conditions when assessing habitability. Venus's role as Earth's twin gone wrong also illustrates how planetary evolution depends on initial conditions and contingencies. Small differences in distance from the Sun, water content, or timing of geological events can lead to vastly different outcomes. Two planets starting similar can diverge completely based on seemingly minor factors. This principle applies to exoplanets as well. Planets orbiting in their star's habitable zone might still become uninhabitable if other conditions aren't favourable. The history of Venus exploration teaches lessons about scientific persistence. The Soviet Union's Venera program endured many failures before achieving success. Each failure informed the next attempt, gradually overcoming technical challenges until landers survived long enough to transmit from the surface. This persistence yielded remarkable results. The first images from another planet's surface detailed atmospheric measurements and chemical analyses of Venusian soil. Modern missions continue this tradition, with scientists and engineers tackling Venus's extreme conditions through innovation and determination. International cooperation in space exploration emerges as another lesson from Venus. While much of Venus exploration occurred during the Cold War with competing American and Soviet programs, later missions increasingly involved international collaboration. Venus Express combined European spacecraft with international instruments and tracking support. Future missions will likely involve even more cooperation, with NASA, ESA, Roscosmos, ISRO, and other agencies contributing complementary observations. Venus, belonging to no nation, invites humanity to work together in pursuit of understanding. Venus challenges our assumptions about planetary habitability and forces us to think carefully about what makes a planet livable. Distance from the star matters, but so do atmospheric composition, geological activity, magnetic fields, water content, and countless other factors. Understanding Venus helps us evaluate potentially habitable exoplanets and assess their likelihood of supporting life. As we detect Earth-sized planets in habitable zones around other stars, Venus reminds us to look beyond simple metrics and consider the full complexity of planetary evolution. The study of Venus contributes to comparative planetology, the discipline of understanding planets by examining similarities and differences across examples. With only one detailed example of habitability, Earth, our theories remained poorly constrained. Venus provides a second data point, showing how an Earth-like planet can evolve along a different path. Mars adds a third example, smaller and colder, but once possibly habitable. The outer planets and their moons provide additional comparisons. Each world teaches us something, refining our understanding of planetary science. Venus reminds us of the importance of continued exploration. Despite decades of missions, fundamental questions remain unanswered. Is Venus volcanically active? Does life exist in the clouds? How much water did Venus have? When did the runaway greenhouse begin? These questions require new missions with improved instruments and innovative approaches. Space exploration isn't a finished project, but an ongoing endeavour, each generation building on the work of predecessors and expanding the frontiers of knowledge. Finally, Venus teaches humility. This planet, so similar to Earth in size and composition, evolved into conditions utterly hostile to life as we know it. The same physical laws govern both worlds, yet outcomes diverge dramatically. Venus shows that habitability is fragile, that favourable conditions can't be taken for granted, and that planetary environments can change in ways that preclude life. As we contemplate humanity's future, whether on Earth or potentially on other worlds, Venus stands as a reminder to respect the delicate balances that make life possible and to carefully consider the consequences of our actions. We've drifted now through billions of years, following Venus from its fiery birth in the protoplanetary disk through transformation from potential paradise to hellish world. We've explored clouds of sulfuric acid and plains of volcanic rock. We've travelled with Soviet landers descending through crushing atmosphere to photograph an alien landscape. We've contemplated mysteries from phosphine to plate tectonics, from ancient oceans to possible life floating in the clouds. Venus remains enigmatic. Wrapped in its yellow-white veil, the planet continues spinning slowly through the cosmos, holding secrets beneath its clouds. Spacecraft may have mapped the surface and sampled the atmosphere, but much remains unknown. Future missions will answer some questions and undoubtedly raise others. The story of Venus is far from complete. What makes Venus so compelling isn't just the extreme conditions or the strange geology. It's what the planet represents: a cautionary tale, an alternative evolutionary path, a mirror showing what Earth might have become under slightly different circumstances. Venus reminds us that planets are complex systems, where small changes can cascade into enormous differences. It teaches that habitability is precious and that understanding other worlds helps us appreciate and protect our own. As you drift towards sleep, perhaps you'll dream of that brilliant star hanging in the twilight, the evening star known to countless generations before us. Behind its beauty lies a world of crushing pressures and searing heat, of ancient volcanoes and clouds of acid. A world that might have been a paradise, that could have harboured life, but instead took a different path. Venus, Earth's twin and opposite, forever tantalizingly close yet impossibly distant. The story of Venus is ultimately the story of how planets evolve, of paths taken and not taken, of delicate balances between extremes. It's written in atmospheric chemistry and surface geology, in ancient myths and modern spacecraft data, and it's still being written, with each new observation adding details, each mission revealing surprises. Thank you for joining this journey through the story of Venus. If you found this exploration relaxing and informative, a like would be wonderful, and subscribing means you'll drift along with us for future explorations of distant worlds and cosmic mysteries. To those already subscribed, your support makes these journeys possible, and I'm grateful for each of you. Sweet dreams, and may your rest be as peaceful as Venus's slow rotation through the eternal night of space. Good night.